Larger than the planet Mercury, Titan is the only moon known to have a dense atmosphere and stable bodies of surface liquid. Its orange haze, composed of nitrogen and methane, conceals a fascinating world filled with rivers, lakes, and seas of liquid hydrocarbons. Beneath its icy crust lies a subsurface ocean of water, making Titan a prime candidate in the search for extraterrestrial life. Its unique chemical composition and Earth-like processes such as methane-based hydrological cycle offer unprecedented opportunities for scientific discovery. NASA's upcoming Dragonfly mission aims to explore Titan's surface in a way that were once the stuff of science fiction. Scheduled for launch in 2027 and arrival in the mid-2030s, Dragonfly will be a rotorcraft lander capable of flying across Titan's diverse terrains. Today, we'll be delving into the logistics of this groundbreaking mission, the rationale behind choosing Titan as a destination, as well as the technical challenges and solutions involved in landing there, as well as the potential for humanity's future exploration and settlement of this distant world. Which brings us to the first question: why Titan? NASA's choice of Titan for their upcoming Dragonfly mission stems from its unparalleled scientific potential. Unlike other icy moons, such as Europa or Enceladus, Titan offers both surface and atmospheric environments ripe for exploration. Its atmosphere, 1.5 times denser than Earth's, provides a safe and stable environment for aerial exploration, while its low gravity allows for efficient mobility. The presence of organic molecules combined with energy sources and liquid mediums creates a natural laboratory for studying prebiotic chemistry and the building blocks of life. Titan also represents a natural testbed for understanding planetary processes. Its methane cycle mirrors Earth's water cycle, complete with evaporation, condensation, and precipitation. Studying these phenomena on the Titan could provide insights into the dynamics of Earth's own climate and geology, as well as those of exoplanets with similar conditions. One of the most compelling reasons to explore Titan is its potential for harboring life. While the surface is far too cold for liquid water, averaging minus 180 degrees Celsius, the subsurface ocean may be warm enough to sustain microbial life. Furthermore, Titan's surface chemistry, rich in complex organic compounds, offers clues to how life might arise in environments vastly different from our own. By landing and sampling various locations, Dragonfly aims to answer fundamental questions about the origins of life and its universality in cosmos. However, this only tackles half of the problem, with the second half being the logistics behind the mission. You see, a Dragonfly is a dual quadcopter rotorcraft designed to fly over Titan's surface, covering distances far greater than traditional rovers. The mission's primary objectives include sampling and analyzing surface materials to study organic chemistry, as well as investigating Titan's habitability and prebiotic chemistry. Next up is measuring atmospheric and surface conditions to better understand local meteorology and geology, and finally exploring potential locations of the subsurface ocean that might harbor microbial life. The Dragonfly will leverage Titan's thick atmosphere and low gravity to make precise and energy-efficient flights. Equipped with a suite of instruments including mass spectrometers, gamma-ray spectrometers, and weather sensors, Dragonfly will provide comprehensive data from multiple sites, including a potential landing near Shangri-La, a region of the Titan characterized by dune fields and organic-rich terrain. Now, speaking of traveling to the Titan, the journey will take approximately 8 years, beginning with a launch aboard a heavy-lift rocket like the Space Launch System. The spacecraft will perform a series of gravity assist maneuvers, gaining speed by slingshotting around Earth and other planets before making its way to Saturn. Once it is in the Saturnian system, Dragonfly will rely on precision navigating to enter the Titan's atmosphere. However, a landing on the Titan presents unique challenges due to its dense atmosphere and low temperatures. The EDL sequence will involve 3 main stages, first of which being the atmospheric entry, second being parachute deployment, and third being rotor deployment. Upon entering Titan's atmosphere at high speed, the Dragonfly will decelerate while being protected by a heat shield specifically designed for this occasion. Then, a series of parachutes will stabilize and slow the descent. And finally, once the craft reaches a safe altitude, its rotors will deploy, allowing for a controlled and precise landing. This innovative approach minimizes risks associated with rough terrain and maximizes the mission's ability to reach scientifically valuable sites. Now, if this were all as easy as we make it out to be, then why didn't NASA do it already? Well, that's because there are more than a couple of issues and challenges that need to be tackled first. First of all, Titan's frigid temperatures could affect the performance of Dragonfly's instruments and power systems. Engineers have designed robust thermal control systems to maintain operational temperatures. Then there's the topic of controlling the spacecraft. With a light travel time of over an hour between Earth and Titan, real-time control is impossible. That's why Dragonfly will utilize cutting-edge tech and operate completely autonomously, using advanced algorithms to make navigation and scientific decisions. But even then, Dragonfly will have an issue because of the completely alien terrain it will work on. Despite data from the Cassini-Huygens mission, Titan's surface remains largely uncharted. Now, sure, Dragonfly's onboard imaging and radar systems will map landing sites and flight paths in real time. That said, NASA's team behind the mission has developed and is still working on a lot of innovative solutions to overcome these challenges. For example, the use of multi-mission radioisotope thermoelectric generators, or MMRTGs, will provide reliable power and heat, while the redundant system ensure a resilience against unforeseen malfunctions. Additionally, Dragonfly's AI capabilities will enable it to adapt to Titan's dynamic environment, ensuring mission success. And with all of this out of the question, there is still something we need to talk about, and that is the future of humanity on Titan. You see, Dragonfly's findings will lay the groundwork for future missions to Titan, including potential human exploration. While the moon's harsh conditions preclude immediate colonization, advancements in technology and deeper understanding of its resources could make long-term habitation feasible. One possibility is the extraction and utilization of Titan's abundant hydrocarbons as a fuel source. Additionally, the subsurface ocean could serve as a critical resource for water and oxygen, essential for sustaining human life, such as pressurized domes or subsurface shelters could provide protection against the extreme cold and radiation. And if the Dragonfly discovers evidence of life or prebiotic processes, it would have profound implications for humanity's place in the universe. Such a discovery would drive further missions to study Titan's biology, chemistry, and potential for fostering more complex ecosystems. Titan may also serve as a launching point for deeper exploration of the outer solar system. Its low gravity and research could support spacecraft refueling and assembly, enabling missions to distant worlds like Uranus, Neptune, or even interstellar space. Essentially, the Dragonfly mission to Titan represents a bold step forward in humanity's quest to explore and conquer the solar system and, in turn, the universe. By unraveling the mysteries of this enigmatic moon, NASA aims to answer fundamental questions about the origins of life, the nature of planetary systems, and the potential of human settlement beyond Earth. Titan's unique characteristics and untapped potential make it a beacon of scientific and exploratory ambition, promising to inspire generations to come.